Okay, we're recording. All right. So Adam Martin, Standard Model Effective Field Theory and Other Effective Field Theories, lecture number 3.
All
Please go ahead.
right. Whoops, hold on a second. I'm making sure I've got the chat window open so we can do this. Welcome, everybody. Good morning or afternoon. It's good to be back talking to you. Like introduced, this is lecture number 3. And lecture number 2, I promised, was the most technical. We went through lots of how we would do RGEs for EFT coupling. There were lots of messages in there. A couple of takeaways would be treat an effective field theory, not as some low energy reject of a real theory, but as a quantum field theory in its own right. And by doing so, by picking a smart regulator in DimReg, you can really separate and order perturbation theories in a really nice way. You can keep fixed order in your EFT power counting, sum up lots of other effects. And in the example we did last time, we had sort of our fermion interacting with a heavy scalar, and then we had like a photon. We could sum up all loops of that photon's effect. So I was going to say a few words about that, talk a little bit, just sort of cleaning up about some other loops. Sure, we did loops of photons, but that's not the only thing around. That will sort of establish the last technical things that we need to then apply what we've learned about EFTs to a couple of scenarios. First is the EFT perspective on the hierarchy problem, and then all of these EFT ideas apply to standard model as an EFT. So as always, shoot questions at me. We'll get a break partway through. Yeah, and fire away. So just a reminder, right, we're exploring all of this, still doing top-down EFT, right? I had a theory, I matched it, I'm worrying about now how I do that matching and the benefits of working just in the EFT. So we got our full theory, right? Our light fermion's the light field, heavy scalar, a poorly chosen coupling between them, kappa, especially if you're gonna use loop momentum K. I will try to be neater handwriting about that. And our EFT is just this theory that is just a fermion, higher dimensional operators. So as I was talking, sort of just recapping, we've now explored matching, and now we've explored how in an EFT I can do running. And that's basically, of course, yes, there's details and complications, but that's really it. What I mean by that is we can just rinse and repeat this procedure across multiple scales and multiple EFTs. So imagine my favorite diagram, energy here. We had a mass of some kind of particle. This is sort of more abstract than our actual example. I'll get to the actual example again. Then there's a second scale. And we say we have our full theory here. We can just, as I said, rinse and repeat. We would run down our full to that scale, M2, match to an effective theory, call it 1, that doesn't have M2 as a propagating particle. We've encoded the effects of M2 in coefficients. We would then run within this L effective 1 down to the next threshold, M1, integrate out M1, match onto yet another effective theory, L effective 2, that doesn't have M1, nor does it have M2, and we would keep running here. This we could proceed. This is exactly how you want to organize calculations to make sure that you don't have really loop soup, that you've summed up all of the perturbations of something and maintaining our power counting in things like P over these M's. And as we talked about a couple of examples when we were visiting operator mixing, this is exactly what you do in, say, theory of below the massive W Higgs, et cetera, when you just have, when you're trying to do heavy meson flavor sort of physics. This is exactly what kind of physics we do. So, very nice procedure. What we're doing is really tackling one scale at a time. This was a whole procedure. We're not ending up with weird, funny logs here, just by tackling one at a time. So, sort of right up here, there are other loops. Specifically, we match these theories at tree level. Right? We may remember way back in lecture number 1 that we kind of said, here's our full theory, and we somehow equated that to that vertex. And this coupling here was our kappa. So this matching involved kappa squared. We can improve this. The whole idea of EFTs is that they're systematically improvable. You want to go to a better order, it might be more complicated, might be a lot of work, but you can do it. So we could also match at loop level. This may be because, which is going to be order kappa to the 4th. We may just want something more accurate in kappa, or it may be that there is no contribution from tree level. Certain theories, I just don't have this kind of, we just put in a simple toy where I did have this. You're not always guaranteed to have this. So what we want to explore is just sort of what's involved here. We're not going to actually do this. This is would involve lots of loops. Promise I'm not going to torture with loops. We're just going to talk through this procedure because it's then going to be useful later on. In drawing these diagrams about how we're going to match, I'm going to use our good old theories here, but I'm going to make my life a little bit simpler here, and let's forget this gauge piece. What I mean by that is we had made these guys covariant derivatives, so I had this photon loops that I could deal with. Let's forget that complication. So this is just a theory where my only interaction in the full theory is that guy, fermion, fermion, heavy scalar. Well, we can just, at a diagram level, right? Not the only way that we know to integrate out things, but just a simple way. We can just write down the diagrams that are going to be there to order kappa to the 4th in our tree approach, or in our full theory and in the effective theory, right? Effective theory, right? We already know that one. We're also going to forget the momentum dependent piece, right? So that's one simplification. Forget the momentum dependence piece, is I'm really just going to shut this thing off. Again, you could include this. It's just going to add complications that we don't need to deal with. So full theory. I now want to match psi, right? We're matching a process, and it's at some scale. Which we're going to want to set to be around the mass of the heavy particle. I want to write down all the diagrams that appear when I'm doing this out to kappa to the 4th. So sure, we've got the tree level piece is still there, right? And we're going to also, I'm not even going to write the diagrams for the alternate ways of writing the legs, just because we all know it's there. It's not going to add anything to the calculation. There's a tree level piece. Then we have loops. Well, loops, the only extra particle around is that heavy scalar. So the loops that we're worrying about matching, or that we're worrying about right now, is things like this. There's a box. This is obviously, this is our kappa squared. Here's kappa to the 4th. And hey, I could draw all sorts of other diagrams that involve this. There's a bunch. That's what, at least diagrammatically, we've got for fermion, fermion to fermion, fermion in our full theory. There are loops. You could do some naive power counting of these loops, just sort of momentum of the loops going around. And you would find that these are, some of them are divergent. If we want to focus on one, we could have somebody like that. Right? These include divergences, right? But we're not going to worry about that right now. We'll get back to it in a second. So even in the full theory, some of those loops would blow up or would appear to be divergent, which we know, or which we've encountered lots of times. EFT, what's the calculation? Same process. Well, here's my tree level piece. And I'm going to have loops, things like that. Right, here is that vertex. Remember, we're working in an EFT where I've shut off that D interaction just to make my life less complicated. And I only have that C interaction. By forgetting the gauge piece, I'm just saying we're no longer going to have charge this thing under a light U1. Just go back to the theory where it's a regular derivative. There are no photons around. My effective theory is just really this guy, or it just involves D slash, right? So the gauge I put in there because I wanted another interaction to show how I could stick to a given order, k squared over m, or kappa over m squared, and sum up the effects of that other interaction. We're moving on from that and just dealing with higher order in this one interaction. Okay, fantastic. So, right, just with that one C interaction turned on, I'm drawing my loops in the EFT. So I've got that guy, this one, I'm also got pictures like this, et cetera, et cetera, et cetera. And you want to match these, right? That was the whole procedure. The whole idea of the EFT, separate theory, only the light degrees of freedom, and you dial its inputs such that it matches the full theory at low energies, meaning below the scale of that heavy particle. So I've got to match these. But first, I've got to deal with the fact that, sure, we already said full theory is going to have divergences in it. Right? Those loops are going to blow up. The effective theory, sure, again, we could just count propagators and spot divergences in this. So these are also divergent. So what do? Do we worry about this? No. We don't worry about this because what are we matching? We want to match physical amplitudes. Divergences show up as this intermediate step. We get rid of them with counterterms. So the thing that we want to match is not just these diagrams, but also the counterterms that we would have to write down in the full theory and in the effective theory. So let's flesh that out a little bit. So if I was to do this calculation in the full theory, so I'm doing this loop, or all of those loops, we would find it's some number over epsilon, right? There's going to be a divergent piece, and we're using dim reg for all of our diagrams. Plus, there'll be a finite piece. And that finite piece, we know is going to depend on, m, the mass of that heavy particle, because it's floating around in these loops, and the mass of that light particle. Right? If I was to repeat and just calculate these loops in the EFT, we'd get some different number over epsilon, right? We're just doing all those loops in dim reg. Right? Divergences are going to show up as 1 over epsilon. This is going to have a finite piece. And that finite piece, well, the only state around is that light fermion M. So it makes sense that finite piece can only depend on that. And so what do we do in renormalized perturbation theory when I'm calculating a physical amplitude? Well, we know there's also a contribution to these amplitudes from the counterterms, and we choose them to get rid of this stuff. So we know that counterterms so physical amplitude, because it's connected to something I can measure, can't be infinite. If I'm calculating it, I've got to include not only the loops, but the counterterms, and the counterterms are there, as they've always been, just to get rid of any of this junk. It is an interesting point is that this number does not have to be equal to that number. Right? In general, right, this is a different divergences than this guy. Remember, EFT is its own separate theory, hopes and dreams. It doesn't rely on that. So there's no need for this number to be related to this number. So what we actually want to do when we're matching at a loop level like this is compare at our matching scale the amplitude that we've calculated in the full theory plus the piece from the counterterms, such that this thing is all finite. Sorry, let's be a little bit more exact here. These are the amplitude or the counterterms the full theory would have its own z's, and those are dialed to remove those epsilon, because we're comparing physical quantities. And we're going to set this equal to the amplitude in the EFT. And of course, we have to supplement that by the EFT's counterterms, because we want to get a finite physical amplitude in the EFT. So we want to equate those two things. This is going to depend on kappa m m. This is going to depend on c m. And in solving this equation, which I'll put a star next to because we're going to come back to it, or we're going to use it a couple of times, that's the defining equation for C. At tree level, we had something similar, right? C was defined by this, except this would be a tree level on either side, and there's no counter terms. At loop level, we have the same idea. Tree plus loop plus counter term on the full theory side equals tree plus loop plus counter term on the effective theory side. Solving this gets us C as a function of the UV theory parameters. In practice, complicated to do. It would take pages and pages of dim reg stuff to do, but this is the idea. So yes, we can systematically improve. This is how we would do it. Key point, take away nothing else, is that we want to say that the physics is not in these guys. Those are just removed whenever I'm comparing physical things. There's a little bit more info that we can say, and I think it's kind of valuable to include. Just what kind of stuff can appear in a loop, right? Forget the pole, the 1 over epsilon stuff. We know I'm going to subtract that out. But what's the finite stuff that can appear? Well, in this guy, full plus, this guy could depend on log m squared over mu squared. Here, mu squared is that matching scale we're carrying out the calculation at. Or it could depend on log m squared over mu squared. All right, got a mass there. Right, in doing this, I'm setting, p squared, I'm doing this, setting those external momentum so that those guys are on shelf there. Right. A EFT. Well, this guy can only have this kind of log in it, right? The only state that's going around those loops is the fermion, which has mass little m. It can't have that big M in it. It's not in the theory by design, right? Big M, this guy can only have the propagating degrees of freedom. Capital M isn't one of those. So the full theory can depend on some stuff. The effective theory can depend on fewer things. In addition, these must agree. The whole idea of the full theory, or the whole idea of the EFT, is it captures the physics of the full theory at low energies. Therefore, it has to reproduce the same behavior in those logs, because this is all low energy physics behavior. These things have to be equal, meaning the actual number and form that shows up in front of this log in some nasty, horrible loops here has to be exactly equal to the coefficient or times the log of little m over mu that shows up in these loops here. By design, low energy physics has to be the same in those two. What does that mean? Well, it means any of this, if the little m over mu dependence and this calculation match, it's going to drop out when I try and solve for C. That makes some intuitive sense. The whole idea is that we want to absorb all of that UV physics stuff into the coefficient, all of the infrared stuff, that's got to be the same. So it would be a little bit funny if that UV coefficient had any dependence on that infrared stuff. If this thing can't show up, that means that matching say this a better way, that this guy is the only thing that can show up in the matching. So when we match our theory at kappa to the fourth instead of kappa squared, when we did it at tree level, we had C was kappa squared over M squared. Once we've done it at loop level, we're going to have obviously that tree level result. The new stuff we can get is the only kind of log that can appear is that mu squared or capital M squared over mu squared. Now, you've been very nice and no one has raised the question. There is yet another alternative here. What about M squared over M squared? Big M squared over little m squared? This is certainly something that can appear. In the full theory, but you can't break it up. This piece goes to matching. That piece is left. Exactly how this goes, I'm not going to show. This actually does not happen in the simple theory that I've written down right here, but it is something that can happen when you're studying general EFTs at loop level. Is it just the difference of the two logs? Will the infrared necessarily appear in the matching? No, it will necessarily, it has to cancel. The whole idea is those two amplitudes agree completely for the all IR stuff. Could it not appear in the calculation? No, it's going to cancel out in this starred calculation of the matching. Yes, that's just the difference of the two logs, but exactly how it's split up is not quite as simple as what I just said. Right? I'm not going to go through this. There's a very elegant and very detailed, very, very nice discussion of how this separates. This is in Tim Cohen's lectures, right? It is not quite as simple as just writing that thing into two parts and shuffling one into one and one into the other. But it is something that can happen if you're properly dealing with things where I'm matching correctly, and it will disappear, or it will separate nicely. But I'm not going to devote any more time to it, but I would for you, this is a very, very nice discussion. Okay. So that's about it, just for our sort of technical parts of loops. We've seen them running, we've seen them matching, we've seen running our matching at tree level, we've seen matching at loop level. We want to talk about, sorry, I usually stand up when I'm teaching. Sitting down is even worse than doing things on video. I gotta like move around. So this is why I'm hopping around in my desert island here. So I hope that is not ultimately distracting. I want to move on to a different subject, which is, so far we've always seen heavy physics decouples. Right? I can do this EFT program. The UV physics is shuffled into the inputs of my parameters of the EFT, behaving as 1 over m squared kind of thing. This works. This idea that heavy physics decouples, except when it doesn't. So decoupling works. Right? Nobody, I take M, capital M to infinity, and those effects of UV physics are not lingering around, except when it doesn't. And where it doesn't is scalar masses. There's a couple other situations where it doesn't, but this is the most, well, let's erase that. Let's concentrate on the case of scalar masses before we get distracted. Right? Why is this important? We've got a scalar in a standard model, and we'd like to understand its mass. We'd like to understand how to view its mass in as many different ways as possible. And you have all seen, I guarantee, you have probably all given, I am very guilty of giving this argument myself, the following argument for the Higgs boson. Here's a Higgs, here's a top quark. You do this loop, you say that's -3 d4k 2 pi 4th. There's some Dirac stuff. The end, you do this loop, you do it with a hard cutoff, and you're going to find that this is -3 yt squared, lambda squared, again, our cutoff that I put on there, 16 pi squared. And what do we say? We say, aha, there is evidence that we have to have new physics. Because that loop diverges, we have to have new physics. Right? We've all given this argument. We've all seen this argument. Put it in the chat if you're like, no, I've never seen this argument. I have no idea what you're talking about. We use this to say, oh, there has to be something else going on because look at this. This thing is sitting right there. Oh my goodness. While there is the spirit of that argument is correct, this calculation as a way of motivating it is bogus. Right, we will see that there is sensitivity to high scales, but the divergence of an integral is not that case. Right? We can see some hints. What did I jump up and down and scream at you last lecture, right? Regulator is an intermediate step. This is a cutoff. We could do it in dim reg. Right? We know nothing physical depends on our regulator. And right now, we're sort of staring at the middle of a calculation and going, warning, warning. Right? That's not fair to do. In dim reg, it does not look like that, for example. In dim reg, you'll get something that looks like it's got to be a mass. The only mass around is that guy, the top mass, right? Because I'm imagining this is my top quark, right? Problem, physics should not depend on your regulator. Right? So taking this to the bank and saying, this is why there's got to be new physics, dangerous. So in order to see what the right argument is, we're going to use our same toy theory, but I'm going to juggle a couple of things. So the theory that we want to use to look at this, let's do L full. Basically, I'm going to reverse the order of the masses. I'm going to make the fermion heavy. I'm going to make the scalar light, and I'm going to give a self-interaction for the scalar, just to make life a little bit more interesting. And let's make this guy, capital M is now the fermion mass. Plus a half d mu phi squared minus m squared. I'm going to be very careful and put m squared f there for the mass of that scalar in the full theory. And I'm going to put this, well, let's put it, if we have our other interaction. Right? That's that Yukawa interaction we've had forever. And now I'm going to add to this just a self-interaction among those phi's. Right? Self-interaction among the phi. I want to take this theory, imagine it below the mass of my fermion. So my effective field theory is just a theory of the scalar now, right? Different than what we've done, but we're now pros at EFT. We can imagine this. So this is just going to be a half d mu phi squared minus m squared e. I'm being very, very careful to denote the difference between the mass of the scalar in the full theory and the mass of the scalar in the effective theory, and we'll see why. And there's going to be a, in general, slightly different quartic coupling, and that list would go on and on. Right? So what do we want to do? We want to study this problem in the context of our EFT. So here's our plot. Here's our mass of that fermion. We would match the two theories here. And then in order to see if there's any sensitivity to that high scale, we would want to calculate the mass of the scalar at some low scale down here. Right? So we'd match the theory, then we'd see what's the mass of the theory, what's the mass within the EFT way down here. I'm going to do this two ways or in steps, because I think that really highlights what's important. So first, let's imagine that kappa is 0. So we're going to imagine temporarily shutting off that interaction that connects fermions, the heavy particles, to scalar. Now, totally legit to do, but I'm going to turn it off for now, and we would see what would happen. So here, in the full theory, the only vertex is this guy. In the EFT, the only vertex is this guy. Well, first we would match. We can just match right at tree level. That's just mass of the boson in the full theory equals the mass of the boson in the effective theory. Yes, we'd say like this is totally obvious. There's no interaction, of course. Right. We're doing this to lay the groundwork because that's not always going to be the case. Right, so the purpose of matching is to solve for the effective theory couplings, masses in terms of the full theory. That just tells us m squared in the effective theory is the same as m squared in the full theory. There's no interaction. Right, or there's nothing that I'm integrating out that's different in the full theory and in the UV theory. Now let's add loops. Or, just more generally, our quantum correction. And this is within the EFT. So that's this diagram. And we know in the EFT, this is that guy, that coupling right there is what we had called eta. If I go ahead and do this loop in dim reg, this is going to give me well, it's divergent. Yeah, no kidding. But we're doing this in dim reg. We're all okay. We can see a couple of things. First, dimensional analysis. The only mass scale around is m, the mass of that light scalar. Therefore, this loop diagram has to be proportional to m. No other scale around. Divergent, but it's all in that 1 over epsilon piece. And we've got some usual scale dependence that comes on when we're doing a dim reg calculation. But what do we do with the divergence? What did we do in renormalized perturbation theory? Is that an E in the log? Yes, sure. This is m squared E, of course. Yeah. What did we do in renormalized perturbation theory? Well, we know that there is a counter term in our effective theory, which we dial, and it's going to eat up that divergence. So we know in any physical calculation, which is really going to be this guy plus this guy plus the counter term that we put in, that's going to be finite. So in this theory, right, we matched in this weird example where the heavy field didn't talk to the light field. We then calculated loop in the EFT of only the light field, and we find that the net sort of mass of the light scalar at this order is going to be something like m squared E minus eta over 32 pi squared, m squared E. So this, we can think about it as an approximation to the mass at some low scale. Right? We haven't solved the full RGE yet. So we match the theory here, we calculated a loop to try and sort of give us a proxy of what the mass is at some much lower energy. And we see it is proportional to the scalar mass that we started with. So if the scalar mass, if ME, which is really MF, so that if that scalar mass that we put in happened to be small, all corrections to it are also small. There is no M in this equation, no heavy scale. Right? We had a fact that the integral was divergent. That didn't cause any sensitivity to high scales. We dealt with that divergence in the way that we've always dealt with divergence in the normalized perturbation theory, sucked up with a counter term. It did not matter that in one regulator, the 1 over epsilon pole, it didn't matter that if we had done it with a different regulator, we would get capital lambda, our cutoff squared. Right? We know the regulator stuff is just the intermediate step. This stuff gets subtracted out. In this example, with that case true, the mass of our little scalar, there's no idea that capital M is there. Does not care. So the fact that the integral and intermediate step is divergent is not the cause for any problem, right? There's no sensitivity, right? No M here. All right, let's repeat with kappa not equal to 0. Now we want to match again. This is a loop level matching, right? Which is why we had to speak at the beginning of this lecture a little bit about loop level matching. What's happening in the full theory? I guess we do want L full. Well, concentrating on scalar effects, we would have, here's a loop that can show up. Obviously, I can still have the tree level diagram. Here's a loop that can show up. All right, and I could also have this loop still. Remember, in our full theory, there is a quartic interaction. Plus, there's lots of other loops that I could draw that are going to affect parts of the matching that are not just the mass term. So something like this, right? That's certainly there. But what I care about is really the matching of the mass squared term. So I don't need to pay attention to these for right now. It's not that they're not important. If I was to fully match these theories at loop level, I'd have to include this. I would have to include momentum dependent pieces as well. But I'm just zero in on the mass piece, which is, this term, this term, this term. Well, what do things look like in the EFT? Well, we've got this. That's it, right? It was the same diagram that I had just calculated up here. Oh, of course, I still have the tree level piece. So matching says equate these guys plus appropriate counter terms with those guys plus appropriate counter terms. And as we had talked a couple of minutes ago, this term and this term have to appear exactly the same because they just involve the light degrees of freedom. So in the matching calculation, none of this is going to show up. So the matching really is going to be, here's M squared effective theory, here's M squared full theory plus this loop equals M squared effective theory. That is now our matching. Right? So we add these guys, add their counter terms, because I always want to compare physical amplitudes, equal them to L effective theory physical amplitudes. This loop, if we go ahead and do it, all right, this is going to give us a minus for good old kappa squared, kappa, right, that Yukawa coupling that's coming in here. Heavy fermion mass. Right. Yes, it's divergent, but right, we're saying we always want to compare these guys plus their counter terms to these guys plus their counter terms. MF and not equal to ME, that's right, but we're working to a certain perturbative order and all of that stuff. So at least the lowest order, we just if we're being consistent, yes. Right. the differences between them will show up at higher order, but right now we're focusing on the lowest order. So yeah, you're absolutely right. It is going to be important that, but we're going to carry through just like anytime you're doing these perturbative things. All right, yes, the difference is appearing in subleading terms. Gotcha, exactly. All right, let's do this calculation. We don't need to write it out. Basically, it's these two diagrams, killing the counter term, or killing this divergent piece of the counter term, equals this piece. Or m squared in the effective theory equals m squared in the full theory. Once we've gotten our i's, etc., correct, minus 4 kappa squared, big M squared, 4 pi squared, right? Plus there's that log bit that I'm really not going to focus on right now. Right? We can even choose mu, our matching scale, to be capital M, and just remove it. So this piece is the piece that I'm going to focus on, right? Which is technically, that piece. Right. So just to repeat one last time what we're doing this matching physical amplitudes in a situation where there is an interaction between the heavy field and the light field. Do that matching. Again, the fact that things are divergent, this is an intermediate step. We know not present in a physical thing, so we're canceling counter terms here. We also know they have to have the same IR behavior. So loops that just involve infrared stuff, gone. This is now our matching equation. Do we assume ME equals F before? No, ME is the mass of the scalar in the effective theory. MF is the mass in the scalar theory. We're trying to derive one from the other. We've just gotten the relationship between them. But we see that, there's some perturbative order in kappa there to the differences that would show up putting the masses, treating MEs in these loops and MFs in these loops is going to show up at higher order in kappa than we've counted. So yes, absolutely. That's right. The difference in the loops is 0 at one order, but the difference is not 0 at that order. Exactly, very well said. So we are doing matching. Matching is always talked about as a perturbative thing. We're doing this order by order. This is our lowest order matching. Sure, we can put in corrections here, but the important part for the argument is captured just with this guy. Right? And yes, we're assuming the two kappas are the two quartic interactions are the same because they are up to higher corrections in this guy. Right? So here is our matching coefficient. This tells us the mass in the effective theory is the mass of the full theory plus some blob. So in order for m squared E to be much, much less than yes, okay, good. We're all on the same page. In order for this effective theory mass to be much, much less than this matching contribution, this is where we have to have some cancellation or tuning. This is the correct statement of the hierarchy problem. The mass in the effective theory is quadratically sensitive to the scale, the physical scale of heavy particles that it interacts with. Right? The fact that a single loop diagram is divergent, right? That's just an intermediate step. And we saw if there was no connection, heavy scale didn't show up. This is a physical mass of a heavy particle that talks to our light particle. If that's present, then in order to have the mass in the effective theory, much, much less than the mass of that heavy thing, this physics that's not decoupling, this is why we say not decoupling, because this low energy parameter is sensitive to m in the numerator. In order for that to have, there has to be some cancellation going on. This is what we worry about as tuning. Do we mean here kappa need order to be 1 to avoid fine tuning of kappa? There is also, you can make the similar argument about kappa, but this is really independent here, right? You can mean, let's see, do we mean here kappa need to be order 1? We're just assuming, it doesn't really matter what the kappa is. For hopefully, let me clarify this in a little bit. Yeah, what the important thing is, if I had a connection where the scalar talked to a heavy particle, mass of the heavy particle got dragged in. If I don't, mass of the heavy particle does not get dragged in. So let me keep going. If it's still unclear, okay, hold on a second. Why is there a fine tuning or cancellation here? Can't we have ME approximately MF much less than kappa M, right? This is saying if I need this to be much smaller than, here I'm subtracting here. If I want a small number, say this is 1 and this is 1,000, I need this thing to be minus 999, right? That's the cancellation that I'm talking about. Exactly. Hold on a second about questions for the Higgs. We're going to talk about the Higgs very much. Right? We're clear on this cancellation. This is what I mean by cancellation. Sure, even if kappa is very, very small, why M could be very, very, very big, right? Take M to be physics at 10 to the 16 GeV. Right? So, right, I mean, this doesn't tell us a degree of the cancellation, and perhaps there is a reason why kappa has to be very small. I'm just saying that this is a starting of a warning that there has to be something going on. Some cancellate, right? And we can talk about, well, let me not get ahead of myself. But this is the correct statement of the hierarchy problem. It does not come from a divergence of an integral. It comes from matching. Right? So yes, scalars sensitive to particles, but they're sensitive to physical particles. They're not sensitive to just a divergence. So what does this mean for the standard model? I think it is reasonable to make kappa small because of an accidental naturalness of a shift symmetry. Right now we have no shift symmetry. Why should kappa be small? We just take kappa to be order 1, right? You can make a similar argument about kappa. You can have a loop corrections to kappa, which would tell you roughly the size that kappa should be too. We have a mass for our scalar, which also breaks our shift symmetry. So then maybe ME squared much is greater than kappa squared M squared. We're just thinking plug in kappa order 1 here. We can start to think, and you're already, our guys, because we're trained to think this way, wait a minute, there's got to be ways around this. And yes, some of the reasons are coming up with symmetries, which I'll get to in a second, for arguing why that kappa is small or that M is small, that capital M, right? But let's keep going, but these questions are all fantastic. For standard model, what does this mean? Obviously, we care about the Higgs, right? What this is telling us is if only standard model to arbitrary scale, no problem. If there is no other heavy physical scale, there's no hierarchy problem. Said in simpler ways, if I make a blob here, Higgs, if the only mass scale around is the Higgs mass, VEV, this guy, this loop has to be proportional to mh squared. So loop corrections proportional to itself. We're in this scenario. So just the fact that diagrams in the standard model diverge does not tell us that there's a hierarchy problem. If you said, I am content with the standard model to arbitrary energy, you don't have to have a hierarchy problem. Absolutely. You are not crazy. But standard model has other deficiencies, right? We know that the standard model has got deficiencies. Many of you are working on those deficiencies. I'm working on those deficiencies. We all do. So, has other shortcomings. And they are likely, you cannot prove that they are, new physical scales. You just start naming these things. We know shortcomings of the standard model. We can put them down and we say, here, one particular for this school, neutrino mass. Everybody loves a good seesaw model. You put in a heavy particle, you're no longer in this category, right? We did an example where the Higgs got, or the scalar got a correction because it talked to tree level. We can get away with that. That's not the only restriction. It could be that the Higgs or our scalar talks to heavy particles only at loop level. If you find yourself talking at all, you're in this scenario. Sure, that's going to adjust this. If my Higgs only couples to my new particle at the gut scale at 3-loop order, there's going to be more junk in front of it, but still I'm going to have ME should be proportional to capital M. So as soon as there's the Higgs gets any whiff of a new scale, you're in this situation where you would expect M Higgs to be close to that scale or to be related to that scale. Sure, dark matter, shortcoming, could introduce a heavy scale. What about composite scalars like mesons? Do we see large correction to meson mass from high energy? No. That's a very good question. Hold on to that for a second. Right, short answer to that is no, you don't, because essentially that meson ceases to be a degree of freedom above a certain level. But hold on, let me answer that a little bit more correctly, a little bit better when we start to talk about what do we hear about is, solutions to the hierarchy problem. Okay, we've got baryogenesis. We've got unification. I have no idea how in vogue unification is anymore, but we still, of course, then there's gravity. We just really don't understand gravity. We expect, if you start thinking, oh, there's some string theory going on, yeah, there's going to be some new heavy particles up there. You have said that exactly correctly. I completely agree with you, Edward. Yes. Yeah. Basically, the question is, anytime any BSM has any contact, and it can be through a higher dimensional operator with some heavy physics, mass of the Higgs should be sensitive to the scale of that heavy particle. So the fact that the standard model alone is not telling you that there's a hierarchy problem. It's the fact that we expect that there are other physical scales to solve other problems. That's why we think that there's a hierarchy problem. Okay. Sort of related to questions that people have been asking, which is absolutely the right question to be asking, which is, wait a minute, if heavy scales are the problem, why are we then throwing in supersymmetry, twin Higgs, blah, your favorite, composite Higgs? Why are we doing that? Well, to answer that, let's think about why is this not a problem for fermion masses? Right? We said the exception. Heavy physics decouples except scalar masses. Why is it not all masses? So this is our question. The answer here is symmetry. In the case of fermions, if I send MF to 0, mass of the fermion to 0, I get more symmetry. I have a chiral symmetry. The left-handed particles and the right-handed particles don't talk to each other anymore. This is chiral symmetry. Custodial chiral symmetry, I've never heard it referred to that way, but I've sort of got in my brain a specific meaning of custodial symmetry. I tend to think of custodial symmetry in the standard model. We'll talk about custodial next lecture, but to me, chiral symmetry is just, I rotate the left-handed fermions and I rotate the right-handed fermions independently. You could attach custodial if you like it, but I kind of like it. Custodial symmetry, not custodial symmetry. chiral symmetry. That chiral symmetry is broken by the mass. This means all loop corrections have to be proportioned to that one thing. This means fermion blob this must be proportional to mass fermion. Because if I shut off mass fermion, I've got to have the whole mass disappear. Again, this guy controls it. If I set that to 0, all fermion mass has to be 0. Therefore, a loop with as many blobs, heavy particles, whatever you want in there, isn't taking m to 0 for a scalar introducing shift symmetry? Well, did you have a quartic interaction for it? Because no, then you've broken the shift symmetry. But yes, shift symmetry is a way people think about putting in protecting things. That's right. So yes, it's not true that, I can't come up with symmetries. I'm just saying for our Higgs, we can't put in a shift symmetry for our Higgs here. Or you can, but it's very badly broken. So symmetry breaks it, or symmetry prevents this weird UV sensitivity. What on earth is that? Uh-oh. Notability, come back. QED, I don't know what you mean by QED breaking chiral symmetry. Chiral symmetry is a good symmetry. Hold on, let's return. Sorry about that. Notability, we had some questions too. I don't know what you mean by QED breaking chiral symmetry. QED is a left-handed fermion talking to a photon and a right-handed photon interaction. And there's nothing that mixes the two. A mass would have to be what mixes the two. So getting back to our question, I sort of started this discussion about fermions by saying, aren't they a problem? Or we said, why supersymmetry? Why twin Higgs, whatever? Well, we see that if there is a symmetry that I can put in, I can prevent this sensitivity to high masses. And we've already sort of in chat discussions been talking about some possibilities. Symmetry can prevent symmetry to high scale. So let's put in a symmetry. Well, with just the standard model, again, sort of focusing our brain here on standard model and therefore the scalar being the Higgs, there isn't the symmetry that I can put in with just the standard model content. It's not, I don't have the luxury of chiral symmetry. So therefore, to impose symmetry, got to enlarge the theory. And this is exactly what's done in supersymmetry. In supersymmetry, you enlarge the theory, and then there is a symmetry that protects the Higgs. The Higgs is then related to a Higgsino. Higgsino is a fermion, and chiral symmetry protects its mass. Or you say the Higgs is actually a Goldstone boson. That has to be a Goldstone boson of some group. Goldstone bosons have a shift symmetry, presents their mass. But in order to impose that global symmetry, out of which the Higgs is a Goldstone boson, you need to enlarge the theory. And this is where go away. No, I'm not interested in typing. Boy. This is where Susie is here. Here's where composite Higgs. This is where twin Higgs is. Add your favorite idea here. Enlarge the theory such that I can put in a symmetry involving the Higgs that removes the sensitivity to super high scales. So yet again, my favorite diagram. Wouldn't soft Susie breaking affect that mass protection? Right, I'm about to say that, yes. So here, the problem with enlarging the theory is we don't see those extra particles, right? standard model doesn't have chiral symmetry because left and right fermions are charged differently. It exactly has chiral symmetry because of that. Right? This is why you need a Higgs to give it mass. Right? I can't write down a mass, m electron, because the left-handed electron and right-handed electron have different quantum numbers. Right? So its chiral symmetry is very much part of the standard model. Right? If I erase the Yukawa couplings, I can mix up all 3 generations of left-handed fields without affecting right-handed stuff. So what are we imagining here, right? I don't see these in particles that I have to put in to enlarge the theory. So what are we imagining? Well, we're imagining here's our Higgs. We're down here. We have m, let's do mass squared. Here's mass squared of sim. That will be the masses of the particles that we're needing to put in to enhance the symmetry. This is the masses of the superpartners. This is the masses of the extra quarks. This is the masses of the twin whatevers. They're up at some scale. We can't put them here because I haven't seen them. Right? So there has to be some little bit of gap here. And then we could imagine up here, we've got some super heavy, gut scale physics that's going on up there. What we'll see is that in this region, once I include the masses, once my theory includes the particles needed to impose this symmetry, supersymmetry, whatever your favorite is, here we have a symmetry that protects mass of the Higgs from that kind of correction. Right? Sorry, m squared h proportional m squared h is not a super clear thing. Protects Higgs. So just like chiral symmetry, there are no big corrections to the mass coming from any physics above this scale. Instead, we do have this gap here. There's no symmetry here, which means there's nothing left to protect the mass of the Higgs. Wherefore, in this scenario, we should expect m squared of the Higgs is proportional to m squared of the symmetry, of the fields that we need to include to impose the symmetry. So this is exactly what was discussed in one of the chat questions. This is a symmetry breaking, soft symmetry, SUSY breaking mass. We get mh should be proportional to that. So it's sensitive up to here, not sensitive to junk above that. This is why we like putting in supersymmetry. This is why we like putting in composite Higgs. It's not because, hey, let's just put in particles. It's because we are biased to believe that there are heavy scales. And in order to not have corrections to the Higgs be up at gut scale, Planck scale, and to lower so that it is massive TV scale particles, we impose one of these we impose one of these symmetries. Yes, that is why people expect new physics at the TV scale. But we see, well, the argument is not, it's not an equation, right? I can't prove to you. It is because of this bias. We say we know that the standard model has shortcomings. We expect or we believe that it is likely that to address those shortcomings, we have to put in new particles, new scales. Hey, that's how I always address the problem. Got a problem, put in a particle, right? So this says to address these problems, we're going to put in a new scale. And as soon as we've done that, as soon as the Higgs gets any scent that there's a heavy scale around, its mass is going to should be proportional to it. For composite Higgs, we don't need to impose symmetry. For composite Higgs, you're saying that the theory approximately has some global symmetry, say SO5, and that breaks to SO4, and therefore I need to put in particles to put things into complete multiplets of those symmetries. Right? Yes, those symmetries are broken. Right? If there was an exact spontaneous breaking only, the Higgs would be massless. Right? So in the case of composite Higgs is a bit more sort of delicate. We're happy to talk about it. But the logic is the same. There should be, we had to put in new things. And therefore, if you have a new thing in there, above the mass of that new thing, symmetry is great and protects you. But below, you can still be sensitive to it. So we've got a few minutes left. I am happy to continue to take questions on this. Otherwise, I just want to find the pieces of paper where we can start to prepped for thinking about the standard model as an EFT. Question is, so when people talk about the hierarchy problem in terms of canceling top loops, it's not the top loop that's the problem. I would agree with that. Right? The fact that the standard model loop is divergent is not the problem. It's that if there is heavy physics, Higgs should be sensitive to it. Absolutely. Well said. All right. Well, I will be in a discussion room. Unless someone is claimed, I'll be in the mu room because I like muons. So we can talk more about these questions here. So what I want to do just in the last few minutes remaining is sort of shift gears slightly. You know, shifting gears is at the end is like an idiot mistake, but let's, I'm gonna try it anyway, right? So far, we have been very top down. What do I mean by that? Forget this hierarchy thing. That was applying EFT to EFT ideas to this particular scenario. When we were talking about matching, running, blah, 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 the whole idea was I started with this theory, ran, matched to an effective theory, ran, matched. And that gives the impression that EFTs are valuable only when I know the full theory and I can do this sort of cascade down. All right, so this is run, match. This is not true. They are also very valuable from the bottom up. And but they sort of require a different way of thinking about it. So what I want to do is imagine we're in a universe where I only have that light fermion psi. All right, I'm at some energies where I'm doing my experiments where I only have psi. Right, if I'm in that scenario, I don't know what caused it, right? I didn't know what the theory is above it. How do I go about things? Well, you can write the Lagrangian for psi, and instead of just stopping at the renormalizable order, I would include all terms, just like I would if it had been matched onto. So I would write down, let's just be lazy, and say this is the dimension 4 piece, plus I would just write down all possible dimension 6 pieces. So let's see, we would have a psi bar psi squared with a CS, a CP, psi bar gamma 5 psi squared plus CT, psi bar gamma mu nu, psi squared plus dot, dot, dot. There are something like 5 of these, right? So this stuff is all the dimension 6, and I could stop there for a second. Right? What do? I don't have anything to match on to those. How do I do things? Well, you don't need matching, right? What we would go out is just measure. You've been handed this theory. Go and measure. Calculate psi, or measure psi psi goes to psi psi. Psi psi bar goes to psi psi bar. Take angular difference, stuff that you've learned about in Professor Shufang's lecture. You would just go measure these guys. You would have to do a bunch of measurements. There's 5 different things. I've got to do 5 different independent measurements. But theoretically, I can go do it. And once I have all those coefficients measured, I can calculate to my heart's content in the EFT. Now I can't just calculate going crazy. I've only measured these coefficients. Those are only power counting p squared over lambda squared.
Yeah, Adam, is that what's done in chiral perturbation theory?
Absolutely.
Like actually using
that is
measurements?
definitely what's going on in chiral perturbation. Perfect question. I was about to say this, right? Not only can we imagine this in a scenario where I don't know the UV theory, but what if the matching's impossible, right? If I have a theory of pions, I'm not going to look at some QCD graphs with quarks and gluons and calculate what is CS. It's a strongly coupled theory. I can't go do that. I can, however, take measurements of pions, infer what those higher dimensional couplings are, and then go ahead, calculate. Actually, yes, the lattice people are doing this. So sure, I should be careful what I'm saying. Right, yes, the lattice people are doing this matching calculation, but the procedure is I go and measure them, or I get a calculation that's something that doesn't rely on my perturbation theory, and I can go. And as long as I'm happy sticking it order p squared over lambda squared, those 5 things that I've measured is good enough. All right, what if I want to go farther? What if I want to calculate something like this in my effective theory, where this is 2 insertions of those, one of those C's, so CS, CS, etc., CS, CT, right? Am I stuck? No, I would have to expand this theory to include all dimension 8. That would give me a whole slew of other things that I would have to go measure. But once I measure them, I can include the measured dimension 8 coefficient effects plus loops of my dimension 6, and I can calculate successfully to order p to the 4th over lambda to the 4th, and I can keep going. So you do not need the UV theory. UV theory is nice for this matching running, blah, 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 but in terms of the other niceties of a EFT, tackling one scale at a time, summing up couplings while working to fix order in others, this approach works. And this is how we're going to do the standard model. I don't know what the UV theory is, but I can go measure enough things and start to infer what the analog of these guys are. And you're not stuck just measuring them. It's not like you go and measure that and you don't get anything from it. Relations tell us about the UV. All right? So if I went out and I measured and I found that CS was not equal to 0, but CP was equal to 0, CT, all those other ones are 0, hey, that's a hint. We know we could get that from matching, from integrating out a heavy scalar. So relations among those measured things tell us about the UV. And this is the strategy we're going to use for this SMEFT. We don't know the UV theory. We're going to measure a whole bunch of things, and we're going to try and infer what the UV physics is. Some people talk about the little hierarchy problem. Again, a chat question. Ooh, that's a lot of text. I don't quite understand it. The little hierarchy problem I exactly refer to as this issue. Right? We can't get away, even when I've expanded my theory to include new states, from the idea that the Higgs mass should be sensitive to the mass of those other things we put in order to enact our symmetry. So if this thing starts to get stretched such that this makes you a little bit uncomfortable, this is what people tend to refer to as a little hierarchy. All of the best theories predict colored particles with the Weeks theory. The best is kind of a subjective thing, but it's possible to break the symmetries of these UV completions such that the mass scale of the partners is above our current experimental reach. Yep, that's just go away. Saying, you know, LHC gets us this much, and all my stuff is up there. I'm totally in agreement there. But then you have to explain why this hierarchy between the experiment and new physics scale exists. Yeah, absolutely. Yeah, sorry, I didn't quite know exactly how this was going in there. Shane, I know you personally work on twin Higgs, so how dare you say that all the best theories have colored top partner? Right? Because I saw your talk at Pheno. Let's see. We are a little bit after 2. So we're going to use this philosophy. I am measuring stuff, and I'm using relationships among those measure things to learn something about UV. All of the goodness of EFT still applies, but we're not viewing it in this running and matching picture. It's more a measure and extrapolate up. So in an hour and a half, you can hang out with me and talk about, actually, we don't have to talk about physics at all. Whatever you want to, I'll be in this Mu room. Otherwise, I will tell you about the SMEF tomorrow, same time. Thanks again for your attention. Great questions. One last question. Is doing loop calculations in this bottom-up fashion useful? Yes, absolutely. And that will become clear when we are doing the SMEP. Short answer is that I'm going to measure some combinations of these C's at one energy. I'm going to measure other combinations at a different energy. Say one energy is the LHC, and one energy is a, low energy electron fixed target experiment. Those are not the same, right? One's 13 TeV, one's, 10 MeV or whatever we're doing. In order to connect them, I have to know how the operators mix among each other. And in order to do that, I have to know loops.
Great, thank you, Adam. Is there any update from the organizers about plans for a group photo? Do we want to try and do that today in the coffee break, or do we want to push it tomorrow so that people have more notice of when and where to show up? I don't know, Ethan, do you want to weigh in on this?
I think we are thinking about doing it during the coffee break. It might be better to hold off till tomorrow, so announce it today and do it tomorrow.
Okay, I think that sounds reasonable, because if it's only an hour and a half from now, people might not get the memo in time if they're not connected right now. So yeah.
Okay, so we'll make an announcement later today.
Also, this way people can wear like their favorite shirt or something tomorrow.
Mm-hmm.
All right, great. So coffee break at 1:30, and I think Adam said he's going to be in the Mu room, and
who doesn't like
see if we wind up with a couple of other lectures as well. And last lecture of today starts at 2, and that will be heck, I have no short-term memory anymore. Laura with perturbative QCD calculations.
Did not mean to slight lattice. Yes, I know that you guys are calculating.
Yeah, but it's hard, right? Like chiral perturbation theory has been around since, I don't know, the 70s, 60s. How long has chiral perturbation theory been around?
I believe, yes, 60s. Gelman-Low theory of, pions and nucleons, 1960 or so.
Yeah.
Everything goes way back, but the classic papers are from the mid-1980s.
Okay.
Yeah, that's the Gasser-Lloyd-Weiler stuff. Yeah.
Yep.
Where they really figured out how to do it, loops and everything.
Awesome. Yeah, I've heard that nuclear physics people are doing effective field theory type stuff as well for trying to handle, like,
yes.
I don't know, matrix elements of large nuclei by taking part of the inner shell kind of and treating it as a thing, and then doing perturbation theory on the outer nuclei.
Yeah, that's effective field theory from hell. Okay.
Yeah. Oh, absolutely.
Yeah,
As you run down from the weak scale down to a QCD scale, and then you try to calculate matrix elements in the nucleons. Then you have to get the nucleons into the nucleus, and there's at least 2 levels for that. You have to get, you go down to the pion scale, and then you have to go down below the pion scale.
If you thought single hadrons were hard, just wait. Yeah, no, that's amazing. Anyway, but those things are important for things like the nuclear matrix elements for neutrinoless double beta decay that we heard about last week.
Absolutely. Yeah.
Okay, great. Have a good break, everybody, and
Yes.
talk to you soon.